Hello. Hello.
Waiting for drinks after the poster session.
Is there anyone online?
It's the V-Fairs.
Oh, VFairs.
The people who are managed.
Okay.
So they do a test for cryo. Hello? Question mark?
And that's gonna be after the poster session.
Yeah,
The
at
drinks.
Goose Acres.
So there is actually a party today at Goose Acres, I think.
Yeah, the Hawaii party. We're just gonna grab one table.
Okay,
So,
I mean, if all the Poltergeist students go and
Hello, everyone, and welcome to the Martian Cryosphere session. I'm Stefano Nerossi, one of your chairs. I'll let my co-chair introduce herself.
Hey, I'm Anna Grau. Welcome, everyone.
And
I'm Racing Cleveland. I'm the moderator.
so a quick mention of our schedule. We're gonna have 6 presentations back to back, 10 minutes each. So for the presenters, let's try to be on time. We're gonna be strict about the 10 minutes. So if you reach your time limit, we are gonna kill your presentation because we need to move quickly. After that, there's gonna be 25 minutes of Q&A. So keep your notes ready with any questions that come along this next hour. We are gonna have a moderator looking at online questions. So if any comes through the online folks, we can manage that. A reminder that we have students competing for the Dwornik Award. So if you're a judge, pay attention, come be ready with questions. And if you're not a judge, I think you're still in time to become one. So be prepared with questions as well. No pictures or videos unless the presenters tells you to take pictures or videos. And the ambassadors can post some written content of your presentation. Unless you don't want to, then you have to explicitly say that. And there is a poster session tonight about Mars Cryosphere and many other topics. So make sure to make it.
I've been told to remind grad students there's drinks after the poster session at the Goose Acres. And I think we can start in 1 minute. Presenters will have the clicker to advance the slides on podium. Wonderful.
Yes, and a reminder that the laser pointer is not visible online, so make sure to mention what you're pointing at.
And I think with that we can.
Yeah,
Yeah.
just start.
So the first speaker is going to be Marie Azevedo, who is going to talk about the identification and modeling of Luth crater autumnal albedo features. Take it on.
Okay, thanks Anna for the presentation. So I'm Marie. I am a PhD candidate at the University of Bern in Switzerland and also a member of the CASIS team. So CASIS is the high resolution imager on board ExoMars TGO. And most of the picture I will show today are pictures from CASIS. So before starting, I would like to give you a short introduction to Laos, which is an impact crater located in the north of Mars. And there is an ice mound in the center of the crater made of different units. So the first unit is a dark sand dune field. Around this dune field, there is irregular and trough-bearing ice, and this ice is relatively bigger in the center and smaller in the edges. And at these edges, there is also very visible layering, which is quite interesting because these have most likely been formed through cyclic atmospheric deposition, so controlled by the obliquity variation, so just like the PLDs. So this, of course, suggests that the mound has likely been formed through successive atmospheric deposition rather than something else. And 3, it's then both a recorder of past climate condition while still being sensitive to any ongoing changes on Mars because directly exposed to the atmosphere. So these taken together make Laos a prime location to study icy processes with different boundary conditions than the main cap. So now I will show you the observation that got me started in this research project. So this, you can see in this picture, a patch that is darker than the surrounding, and the patch is circled by a brighter halo, and there is also a redder spot close to the layers. So these kilometer-sized albedo features have been observed with CASIS at the autumnal equinox of the Mars year 36. And 10 sols later, so you can see here in red the previous extent of the patch. You can see a very notable progress of the patch. So this thing is dynamic, so it's quite interesting. And these have not been described in the literature before. So first thing I did is try to look in other imaging data sets, so IRIS and CTX, to see if we had other examples of that. And answer is yes. So this is an example in 2023 with IRIS, so you can see quite the same morphologies. Another example in 2016, this time with CTX. And if we think again of the observation of CASIS, and if we go 1 year later, so in 37, you can see the features are now completely not detectable in CASIS colors. So that's quite cool in itself. So this got me to my research question, which is, are those recurring albedo features resulting from textural or compositional changes, or both of that? And what is the relationship to the layers of Laos and hence the climate record inside? So I split my question into 2 different parts. So the first one will be try to assess how many spectral units are there in the images. So is the patch spot in halo spectrally distinct in CASIS colors, and in which ways? And the other question is how can we interpret those spectral units in terms of evolutions? So 2 methodological tools for that. First, clustering algorithm in the 3D spectral space, and then simple Apke reflectance modeling to interpret the variation. So the clustering algorithm will be k-means based, and this segmentation will suggest us if there is the visual unit we described before correspond to spectral clusters. So every point will be projected in the 3D spectral space, and then the distance between each point, each data point and the centroid of the cluster will be computed. And then we will repeat that until we found the best compactness and separation of every clusters. And the output of the algorithm will be color-coded spatial maps that project the spectral cluster onto the geographical space, which will allow us for direct comparison between the spectral clustering and the geographical units. So here is the results for the 36 observations. So in the very left-hand side, you have the albedo pictures. So very strikingly, you can see the halo is 22% brighter in comparison to the patch. And the spectral clusters, so you see as colors, quite clearly correspond to the areas we identified before. So the main patch is cluster 7 and the halo is cluster 8. And I did that as well for the summer observation. And this time you see there is mostly 4 contribution, which is the large ice, fine ice, the trough-bearing ice we see in the beginning, and the dune field. So if I now take a spectral profile across all clusters in 26, you can very strikingly see that everything is relatively high in near-to-blue ratio and low in pantone infrared. More specifically, I want you to focus on this part here. And you can see that relative to its geographical neighbor, the patch, halo is even lower in near-to-blue and higher in pantone infrared. So I did also the same thing for the summer. And you can see here that there is a relative increase in pantone infrared for the full profile in comparison to the autumn, and also a relative decrease in near-to-blue. So now the question is, how can we interpret that in a spectral sense? So I use ABKI for that. And rather than doing a massive inversion, I took the distribution of grain, which is the best fit for the low crater ice in summer. And then I pushed that distribution of grain size to bigger ones, and I gradually increased the dust content, the dust fraction. Then I compute the BRDF using ABKI for mixed media, and convolve that to the Cassis-Pan blue and near infrareds to compute the theoretical pan to near and near to blue ratio to compare that to the observation. So stay with me on that. That's the important plot of the presentation. So the x-axis will be the pan to near infrared ratio, and the 1 will be the near to blue ratio. I will use symbols to represent the grain sizes. So 100% will be best fit distribution for Laos. And if we go up, it's the smaller grain size, and down to the stars, it's a bigger grain size. I use colors to represent the dust fraction. So clean ice will be in red and dusty ice will be in purple. And you can see that the non-contaminated ice in red is relatively high in pantone infrared and low in near to blue ratio. And reverse thing, the coarser and dust contaminated ice in purple will be higher in near to blue and lower in pantone infrared. So that's for the compositional and textual scenario. And if I do the exact same exercise, but just looking at the grain size that is increasing, I see the same trend. So coarse ice is high in near to blue and low to pantone infrared. So going back to the observations, we saw that all areas were relatively high in near to blue and low to pantone infrared. And that relative to the patch, the halo was even lower in near to blue and higher to pantone infrared, and also 22% brighter in the albedo. And that is compatible with finer and less contaminated ice in the halo and something coarser and maybe more contaminated inside the patch. So that also the self-cleaning part is really important, because if we can confirm this contamination in the center, is that with the seasonal CO2 cover as a vector or something else? And even with the relationship to the layers, does the supposed contaminant get sublimated back in the atmosphere during the spring or included in the mound during the winter? So future work, now ongoing in my laptop, is that I need to confirm the contaminant presence in the batch, of course. And if confirmed, I need to study the competition between the part that is resublimated and the part that is sinking inside the mound in winter with a 1D exchange model. And if the contaminant is confirmed And if the sinking is dominated, the sublimating part, this could be live polar layer formation, which is absolutely cool to my sense. So next thing, of course, is to submit the full paper to probably ICARIS or PSS. So stay tuned if you want to. And to work for you, if you are part of an imaging team or something, try to observe Laos in between 150 L sub S and 200, and I guarantee you, you will learn something about those. So thanks.
20 seconds wrap up.
Thank you. Tatiana.
Thank you very much. The next speaker is going to be Brian Checkett on non-crater outlier deposits at the poles of Mars as icy climate records.
All right. Good morning, everyone. My name is Brianne Checkett. I'm a first-year PhD student at Purdue University. Today, I'm discussing non-crater outlier deposits at the poles of Mars as icy climate records. So the polar layer deposits, or PLDs, are believed to contain a paleoclimate record. That record is debated, though. However, orbital forcing is believed to be the leading cause of climate change on Mars. So as the obliquity and precession is changing on Mars, it's changing the climate. And evidence of this orbital forcing is what a lot of researchers look for in this paleoclimate. Some things to know about the two different PLDs is that the NPLD is believed to be younger than the SPLD, and the SPLD is believed to be dustier than the NPLD. So similar to the PLDs, there are non-crater outlier deposits at the poles of Mars. They are separated from the PLDs, and here specifically, we're looking at the ones that are not in craters, although there are ones in craters. And they have been identified in some geological mapping as seen here, but they have yet to be quantitatively or extensively looked at as paleoclimate record holders in the same way that the PLDs have been. So we are interested in looking at these icy outlier deposits because we believe that they can contain the same paleoclimate record that the PLDs do, but they could be expressing this record in perhaps a different or more accessible way than the PLDs. And we believe this because previous studies done on ice mounds that are in craters have indicated that there could be this evidence for orbital forcing and this paleoclimate record within the layers. Additionally, these deposits are at lower latitudes, which makes them more sensitive to these obliquity changes. And so we think that these would be really good to look at. An example of one of them is shown here on the screen. So we mapped all of these icy outlier deposits at both poles of Mars using a specific criteria. The first one is that they had to be separated from the PLDs to be considered an outlier. The next and most important is that they had to have significant positive topographic relief. So if you compare the Viking color image here to the Mola elevation with shaded relief here, you can see that the right side of the deposit does not show up with any shaded relief. Like here, you can use the crater as a reference point. And so we're saying that that right side of the deposit is just a frost and not actually a deposit. So we're only interested in the deposit part, and any analysis that we talk about from now is only referring to that topographic relief part. And then layers in these deposits were not a requirement, but they were noted and recorded, so we can do further paleoclimate analyses on them. So we located 13 icy outlier deposits. 8 of them were in the northern hemisphere and 5 of them were in the southern hemisphere. You can see them here on this map. And for each of the deposits, we found the average surface area, average thickness, and volume. And to find the thickness, we took a line of best fit of the surrounding topography, and then we found the difference between that line and Mola elevation. And we did this to find a bottom to the deposit, but also to take into account any background slope that these deposits might be on. And we found that they have a total volume of around 2,000 kilometers cubed. So after locating and examining the exterior of these deposits, we wanted to use radar to examine the interior structure and composition. So we used Sherrod radargrams and cluttergrams. And cluttergrams are simulated radargrams that are made from the surrounding topography, and they show the expected clutter, the clutter that would be expected in the radargrams. So an example can be seen here. but we're interested in the potential bottom of these deposits. So we're looking for things that are not clutter and not only in the radargrams. So an example could be seen here or possibly here. And something to note also is that we only took Sherrod tracks that went through the actual deposit again and not the frost like I talked about earlier. So we found the time delay from the top of the deposit to the bottom of the deposit. And here's another example of one of these icy outliers. This one, however, is in the southern hemisphere. And you can notice that they have, all of the ones in the southern hemisphere had a layer of dust on top, which is similar to what we see with the SPLD. So yeah, we found the time delay between the top and the bottom, and then we found the thickness of these deposits using the same technique I described earlier with the line of best fit. And we use this equation here to find the real component of the permittivity. And we were able to find the real component for 7 out of the 13 deposits. The other 6, we could not confidently identify the bottom of the deposit, so we didn't do any calculations for them. But 4 out of the 7 deposits are consistent with dirty water ice, slightly dirtier than the PLDs. And using a power relation law, if they had a real permittivity of about 4.5, that would suggest that they're about 70% ice and 30% rock if they had a 0% porosity. We also found that 3 of these outlier deposits have unusually low permittivities with a range between 2 to 2.5. You can see the location of these deposits in the top picture there. They're all in the northern hemisphere and they're located right next to each other. So we have some hypotheses to explain these low permittivities. Our first one is that they could be really porous water ice. So solid water ice has a real permittivity of 3.15. But if we increase the porosity of that to 34%, then we can lower the real permittivity to 2.25. And these deposits are only tens of meters thick, so they would have less compression than the PLDs, which could allow for them to have more pore space. Our next hypothesis is that we could have just misinterpreted the radar clutter and we could just be calculating the real permittivity incorrectly. Our next hypothesis is that they could be CO2 ice. CO2 ice has a real permittivity of 2.2. However, we are hesitant with this hypothesis because massive perennial CO2 deposits are not expected to be stable at this location on Mars. However, moraines have been seen nearby that have been hypothesized from CO2 glaciers, and they're right next to our outlier deposits. And our final hypothesis is that they could be CO2 calathrate hydrate, which is a real permittivity of 2.85. So to fully understand our results thus far and the real permittivity, we wanted to look to the complex permittivity, specifically the loss tangent, as that relates to the signal attenuation and can tell us about the material that the radar is going through. So we found the power return at the top and the bottom of all of our deposits, and we used the equations seen here. And we found that all of the deposits have complex permittivities that are consistent with the NPLD. And the NPLD has a range of loss tangent of 0.001 to 0.005, which is also consistent with pure water ice. However, something to note is that CO2 ice is also low loss. But if these were to be CO2 ice, we would expect them to have shallow topographic slopes because CO2 ice on Mars is weak and would essentially flow. And so we did topographic slope calculations, and we found that they all had slopes pretty comparable to each other. So combining our slope calculations and the loss tangent calculations, we are tentatively thinking that these are H2O. So in conclusion, we found 13 icy outlier deposits, 8 of them in the north, 5 of them in the south, and 4 of them appear to be dirty water ice, slightly dirtier than the PLDs, and 3 of them are a little bit more complicated. They have unusually low permittivities, but we are tentatively leaning towards a porous water ice hypothesis. But feel free to let us know if you have any other ideas for us to investigate this, and thank you so much for your time.
Right. Next up, we're going to have our own chair, Stefano Nerozzi, who is going to talk about revealing the structure and composition of the Martian North Polar Basal Unit with Marses. Stefano, take it easy. You still have a few seconds.
Okay.
I'll let you know.
All right. Well, today I'm going to take you to back to the North Pole, and in particular to the lower innards of it, and in particular the basal unit, which lies underneath the North Polar Layer deposits. In contrast, they have very different albedos. The North Polar Layer deposits are high albedo, pervasive layering. Basal unit is low albedo and actually composed of two subunits. One of them being Aeolian in origin, cavity unit. The other one much more enigmatic and the focus of this presentation. So to put them into a timeline perspective regarding their geologic records, we're probably all familiar with the rich stratigraphy that probably records the last few million years of Mars North Polar climate. And for the rest of the Amazonian, we can probably use the basal unit because we know that those two units date back all the way to the late Hesperian to early Amazonian period. Of course, this record is most likely fragmentary due to erosion or lack of deposition, but it still records key moments in the Amazonian period in terms of climate and the surface processes. So there are a few questions that guide our work, and in particular, how are these units related to each other, not only stratigraphically, but in their origin, in their genetic origin? What is their stratigraphy and composition? And what all these parameters and information tell us about past climate? So I'm going to be focusing again on the Rupes unit, which is the most enigmatic of the two subunits of the basal unit. And we know a few things about it. Again, I mentioned the low albedo that suggests a significant lithic component. Thanks to spectroscopy, mainly, we know that there is basalt and alteration products of basalt, such as sulfates of calcium and magnesium. And those are thought by some to be at the origin of the strong gypsum detection that has been detected at the nearby Olympia Unde. And from radar, unfortunately, SHORAD, you just saw it, cannot penetrate through the Rupes unit, but Martian can. And the past studies have identified that it must have a significant ice component. So we are set to clarify some of these doubts and find what is the exact composition of the unit. So I'm going to use MARSES. There was a recently released data set on the PDS that corrects the ionospheric effects on the data that were typically hampering some of the studies at the North Pole because the ionosphere is kind of bad behaved here. And in particular, it has very dense coverage of Planum boreum at 3 different frequencies. So we will see how we can take advantage of this. Very conveniently, the previous speaker introduced a lot of this. I'm also going to look at the complex permittivity. Real part, again, can be determined by knowing the thickness of the unit and the time delay between the top and the basal reflector. For the loss tangent, I'm going to use 2 different methods that have been proved to be valid for a variety of materials on Mars. And in that case, we also need to measure the power at the top and the bottom of the unit. And not only this, but I mentioned that MARSES works at multiple different frequencies. So we can look at the frequency-dependent behavior of certain materials. And very conveniently, water ice has been shown to have a strong frequency dependence in its loss tangent at MARSES frequency with a significant decrease between 3 and 5 megahertz that is not really observed for most other lithic materials. So if we detect this, then we have a clue that there is a significant water ice component. So getting to results, the real permittivity shows a pretty wide distribution centered at around a value of 4, which is pretty close to ice, which is 3.1, but it signifies that there must be something else in there. The wide distribution is most easily explained by the heterogeneity that we observe through the Rupes unit. So for the online folks, if there's anyone, I'm going to point at the lower maps. And in particular, hyperboreal ingula in all frequencies seem to have a much higher permittivity than the rest of the Rupes unit. So for the loss tangent, I'm going to focus on a subsection of Rupes that seems to be showing a more consistent permittivity. Otherwise, I would have a very widespread plot like this one. And what we find is that on average, the loss tangent is fairly high, much higher than the one expected from ice. You just saw that ice typically has values of 0.001 or close to that. We are finding values that are at least 10, 20 times higher than that. So this signifies that there must be a significant lithic component, probably also lossy materials. At the same time, we see clear signs of frequency dependence because the 5 megahertz loss tangent is significantly lower than the 3 megahertz one. So there still must be significant ice within this unit. On average, the high loss tangent explains why SHRAD cannot penetrate through it. The frequency is a little bit too high, and when you calculate the signal-to-noise ratio, it just doesn't work too well for the RUPES unit. And in particular, we find very high loss tangent values, often exceeding 0.03 for hyperboreal lingula, again signifying that there must be a significant lithic component there. So how to put this into an actual composition, because we can't easily read complex permittivities. Well, I constructed ternary diagrams, in this case with water, ice, gypsum, and just regular basalt, not altered. And the overlap between real and loss tangent is very small, signifying that probably we are not looking quite right at the right mixture. So to get a better fit, I have to swap basalt, for example, with weather basalt products that have much higher loss. And in this case, some of the best fits for the aligned Fox, I'm pointing at the top of the last ternary diagram, we find that the ice component is actually close to 85 to 90%. So most of the RUPES unit is made of ice, and the rest is a mixture of weather basalt products that, again, have been detected spectroscopically, so that is not a surprise, and potentially gypsum. So the next question is, where do these come from? So two possibilities: either they were transported from somewhere else, which is a possibility, but these materials have not been found elsewhere in the neighborhood of the North Pole. So I personally tend to favor the second possibility, second hypothesis, which is in situ alteration of basalt within the ice, which has been demonstrated to be a possibility for the overlying North Polar layer deposits. And again, RUPES unit is 3 billion years old. So even if it's very cold and these processes are very slow, it can still happen. 3 billion years is a very long time. In terms of stratigraphy and the structure of the basal unit in general, again, Marses can penetrate through the RUPES unit, but also show us the contact between this unit and the overlying cavity unit. So we can use that to reconstruct the extent and volume of both the units. And so in the left map, I'm going to show you the latest mapped extent of this contact between RUPES and cavity. Elsewhere, it's either only one of the two. And combining this with some of the previous studies, I'm able to show you the first extent and thickness map of the RUPES unit. And in particular, we find that the volume compared to the general basal unit volume is just over 50%. And so this means that not only there is a lot of ice locked up in here, we kind of knew that already, but even if the sediments are only 10, 15%, it's still quite a lot of sediments. Without accounting for porosity, this means roughly a 25 centimeters global equivalent layer of lithium materials that have been locked up in this unit potentially for 3 billion years. So a significant sediment sink in addition to a water ice reservoir at the North Pole. In conclusion, in summary, Marses, and in particular the multi-frequency capability of this radar, can be used to not only highlight the composition, but also the structure of this unit and arguably many other places on Mars. And later on, I'll take any questions. Thank you very much.
Yep.
All right. Next up, we have Isaac Smith and co-authors who will talk about major climate change on the North Pole LA deposits. Whenever you want, Isaac.
All right, welcome everybody to my talk. I want to talk about a climate change we found using charades. So we've seen a couple radar products already today. And I'm also very interested in showing the climate change through that. And let's see, lasers there. We're looking at exposed layers here on the left, and I can't, and there's an unconformity here that shows up and some other layers below that are very interesting. But that unconformity we can track with the radar. So as we all know, the obliquity on Mars changes. As it does, the stability of ice changes. And so at high obliquity, when you have the sun hitting the North Pole a lot, the ice will move away. And then at low obliquity, when the sun doesn't hit the North Pole as much, the ice will come back. And this has been shown in modeling. And also, so in 2003, suggesting that the most recent period, you should have ice accumulation. And also looking back at higher obliquities, the ice should be transported to the mid-latitudes up to millimeters per year, which is quite high. If you look at the most recent part, we should have ice accumulating right now. And so I'm going to review a paper I published almost 10 years ago. If ice is being moved to the pole right now, we should be able to see it. And they suggested up to a 1 meter global equivalent layer. Thanks, Stefano, for introducing that. And so we're going to go look. And in 2016, we found that this is true. We found at about 300 meters, although it's on average closer to 180, there's an inflection in the spiral trough migration that's indicative of a change to increased accumulation. So accumulation that accelerated over time. And we also found there was a transition from an erosional period where the magenta lines are truncations or unconformities at an unconformity. And then the turquoise line here is showing you how we have more uniform conformable accumulation after that. And then the same thing we saw in Geminilingular, where we had buried troughs that existed a long time ago. And then at some point, we transitioned to just this rapid accumulation that just buried them. And so all told, I was able to map out the thickness of this unit that is what I call the widespread recent accumulation package, and came up with a global equivalent layer of about 60 centimeters, which very closely matched the prediction from 2003 of about 1 meter. This is geophysics, so 60 centimeters equals 1 meter. And we started to identify different units in the NPLD and put a timeline on them. This was the first timeline, I believe, on any reflection in the North Pole, in first date. But what about all this other stuff, right? And so if you look back in time, so the blue line is from Lavrard 2007, the black line is from Greva 2011, I believe. They both show that we should have accumulation generally through time, and that if you put a lag deposit on, then you can't sublimate too much ice. But if you ignore lags, you could have massive loss. And so here's on the order of several hundred meters, maybe 500 meters. And then the second one would be a little bit less. And the third one, which is what I would call the wrap, this transition from erosion to accumulation, you should see it measurably. Okay, so what happens with these other guys? I found recently using the 3D charade data set, this was unavailable in the 2D that we had for decades because we couldn't get the right orbital, the geometries, because the orbit gave us just the 2D profiles. So here you can see what might be the best unconformity I've ever seen in my life, ever. And that's including radar, but also in dirt. We lose about 500 meters of ice. This is the wrap, by the way, for scale. So we're looking quite a bit below that. This is the unconformity for people who are online. And this is the textbook version of unconformity. And I think they need to update the textbook because this is not as good as what I just showed. So here we had the wrap above, and I'm calling this the massive ablation and accumulation cycle. The MAC name is pending. And I'm going to call this my example 1 because I'm going to show you a lot of examples. So this is example 1 on the left. This is from the figure in the abstract. Example 2 is on the right. And you can see that there's massive truncations, hundreds of meters of material lost. This is at the margins, mind you. In the center on the plateaus, you don't have nearly as much loss. And it transitions from an unconformity to a disconformity and a nonconformity. And this is all what that means. A disconformity is when you have some kind of separation in time, but mainly it's horizontal. And so I would say that up here you have on the left-hand side a disconformity, then the unconformity, and then a nonconformity, which is this thing where you have just a bunch of erosion that's filled in. Okay. If you look between example 1 and example 2, using the new 3D data volume we have, you can actually create a transect that will join those two. And so here's my example 1, here's my example 2. And if you go all the way across, so we're talking, this is almost 1,000 kilometers of total transect. You can connect these things and show that they have very similar thicknesses and also the reflection pattern. And I do want to point out that we did see this in 2015 with the 2D radar, but unfortunately, because of the geometry, we couldn't see it. But I highlighted it here in green. And I had noticed that there was a truncation there, but we couldn't map it fully. And so now with 3D, we can map it fully. So I'm working on that. This slide shows between example 1 and example 3. And unfortunately, there's a trough I have to cross. So I can't, it's not exactly line to line, but you can see that the thickness here and the reflection pattern closely matches. And so I believe that even though we're crossing this trough, this is the same unit. And here's our example 1, here's example 3, where we have a lot more truncations. And this is at Casma Boreal. So I'm trying to highlight that you can look at this anywhere you want, and you're going to see the same thing. So example 3 I just showed. Here's example 4, which is not quite an unconformity. This is, we have draping on the south but polar facing side of Casma Boreal. And so this is crossing Casma Boreal, which we had never been able to do before, with the perfect geometry, which we can do now. And then example 4 to example 5, we can transition across Gemina Lingula and then show that no matter where you look, the thickness is about the same. The radar reflection pattern is very similar. Of course, there's a lot more stuff going on here that we can't really resolve. And so that's part of the difficulty in interpretation, but this allows us to at least look at the thickness and overall pattern. I can also go around. So this one's really hard to do. It's hard to cross the trough and get a good result. And so if I went from E prime to E directly, I have to cross 9 troughs. This is an advantage that we can go all the way around and only have to cross 2 troughs. And if you look at example 1 and example 6, you'll see that we have about the same radar reflection pattern and the same thickness everywhere we go across the cap. This is my current mapping. It went really fast at first because there's a lot of easy parts, and now it's going really slow. The devils are in the details, they say. And so at the margins, this gets really rough and really hard to map, but I'm working on it. So I put these lines there because I knew that these numbers would need to be updated. So now the 280 is about right, but the 52,000 cubic kilometers is already 65,000 cubic kilometers. And I expect that to approximately double as we go. And I guess I have a little more time, which is great. So we have the wrap. I'm calling this the MAC. That means we should also have a name for the earliest major unconformity. I'm calling it EMU, name pending, of course. I don't know if they'll let me keep that officially. And so I've already shown you the EMU, but you didn't know it. Here's some reflectors that you can see tracking across the cap. And here's some truncated reflectors. So this is being mapped at PSI also. We have a colleague doing that, who's not a co-author, unfortunately. And so here's another example of the EMU, where there's a truncation, and then you can see the layers draping on top of that. And so this was actually first identified in 2010 with the Holt et al. Paper. And so this isn't my contribution, but we're mapping it fully for the first time. Go back. We have the wrap on top, which I don't have highlighted here, the MAC, and this EMU, and then the red line is an important reflector that I care about, but it's for a different figure. And using these arbitrary lines, I can go any way I want. So this is kind of following the C to C prime again. And you can see we can build up a stratigraphy now, matching what the climate record or the climate models say we should have. And we always love it if there's 3 unconformities predicted in the model and there's 3 unconformities tracked in the radar. That means our observations agree. And this is a really fantastic result. And so I think we're really starting to solidify our understanding of the history of the cap to match the models for the first time. Here's just another example of that. I got 1 minute left. Yeah. To highlight again, and then I'll thank you. I'll leave some time for other people. All right.
Thank you very much, Isaac. Next speaker is going to be my co-chair, Anagra Gallofrey, with the influence of MPLD stratigraphy on its absence of flow.
Yep.
Thanks, Stefano. Hello, everyone. Yep, I'm going to be talking about the NPLD certification. And the takeaway messages of the talk are really going to stand for the L in LPLD, as in layered, and absence of flow. Right. So after the talk that we just saw, I don't think it's really needed to introduce what the NPLD is anymore. Essentially, it's a layered ice deposit with ice and dust layers within. Here's some images, and you've seen a lot of this in the previous talks. I'm just going to move ahead. And the interesting thing about this, or at least what I find interesting, is actually the lack of evidence that this large deposit, because we're looking at something that's like a couple of kilometers thick, has really deformed or moved much during its 10 million year history, right? And here's a few examples of how we can see that actually there hasn't been much deformation in this deposit. So first, layers are flat lying. We can see that from stratigraphy. We can see that from radar observations. And this is a very important one because, as I'm going to show later, ice sheets don't do that really. Like, you tend to have deformation, particularly when you move to the base of the ice. And in fact, we lack evidence for deformation. We lack it on the surface. We lack it in the interior. We don't have any significant crevasses or brittle fractures that signify that the deposit has deformed and broken. And most importantly, there's a lack of substantial basal deformation or deformation associated with the troughs, as we saw in the previous talk. And the other thing is that winds and not viscous relaxation of the deposit are the main controls on the morphology of the NPLD, right? So most of the high release troughs have very large stresses because they're like very near vertical cliffs. And still, we don't really see this sort of like upwards bending that we would expect if this was a normal flowing ice deposit. Right. So what I mean by normal flowing ice deposit, I mean this sort of like parabolic velocity profile where most of the deformation is occurring at the base of an ice sheet. So you have to imagine that this is an ice deposit and we're looking at the velocity with depth, right? So at the base, most of the velocity is happening, most of the deformation is happening. And on the top, you achieve the maximum of the velocity, yielding this sort of parabolic velocity profile. So this is an example of what the NPLD would look like if it had seen significant deformation, right? So this is Greenland. And you see all these like falls, jelly rolls, and other deformation structures. And you could say, well, maybe like charade is not precise enough to see some of the like small details in there, but then it would actually show up as like a no reflection zone, which is not what we see either. We see flat lying layers, right? So even near at the base, we don't see these sort of like highly folded structures, which actually means that the thing has just not moved much during its history. So there's two working hypotheses here. One that Isaac actually published in 2024, which says that it's the stratified nature of the deposit itself that actually controls its lack of deformation and prevents it from flowing at a rate that it's observable. And in addition to this, I'm going to add to that, saying that the fact that you have dust-rich layers, particularly the fact that you have them near the base, actually really holds the thing together, and it plays a really important role modifying the rheology, the bulk deformation dynamics of the NPLD. Let's dive in. So to make progress, essentially, like I built a model that it's essentially capturing the ice and dust layer dynamics using what's called the Stokes equation, which are pretty standard for viscous flow, right? And then I took the shape of a dome ice sheet. I didn't look at what's going on at the ice margin. That's going to be for future work. For the moment, I'm just worried about what's going on inside of the ice sheet, even the ice divide. And then what's new here is really like using this Hileshow approximation. This is an approximation that works for viscous flow when it's confined in layers. And these layers actually are much smaller than the total depth of the total deposit. So under these conditions, which actually the NPLD meets very nicely, we can just like vertically integrate. So we take vertical averages of things like viscosity, temperature, and density at each individual layer, right? So this is something that had not been done before. And then we actually analyze layer by layer, and we implement boundary conditions at the interface between each individual layer. At the base of the NPLD, things not moving, there's no water there, so there's no sliding. And then we think that there is continuous deformation between each ice layer. And I'm going to make a distinction here between dusty ice layers and dust-rich layers. Dusty ice layers are going to deform. Dust-rich layers are not going to deform. More on that in a minute. So every time that we have one of these dust rich layers, the dust-rich layer is not going to move, and we have a zero velocity condition. Next up, we try to capture a realistic stratigraphy. So this is based on the models by Lalick and Wittberg and co-authors. And essentially, same thing goes from like modeling the dust content within each one of the layers in the NPLD. And then lately, I assume just like plain conductivity temperature profile. So for those that don't go to bed thinking about the Stokes equation and the Hilly-Shaw approximation, I like to propose two terrestrial analogs. So on one side, we have the cookie dough. This is Isaac's cookies. So I'm going to make a claim here that actually the NPLD does not necessarily follow that type of rheology, and it flows more like a tiramisu cake. So this is a more adequate analog for the NPLD structure. All right. So now we're going to look at what happens when you actually consider that you have dust layers that are messing up with the rheology of the deposit. Turns out that dust actually really complicates things. And we know this from terrestrial permafrost literature. It's actually kind of a problem to understand exactly how the rheology of dust and ice mixtures are going to work. But what we can say is that there's a fundamental difference around the 67% dust content, in which below that, it behaves essentially like something that still deforms, is dusty ice layers. And above that actually has this behavior where it jams and it doesn't deform anymore, right? So this is going to play a fundamental role in understanding what the NPLD is doing in terms of deformation, right? So to make progress, we looked at possible realistic stratigraphies for the NPLD. So we looked at both modeling results from Wittberg and from observations from Lalick to build essentially like similar dust fraction profiles that mimic this sort of like Poisson distribution. And here, this line that I'm showing here, it's going to be the 67% transition in rheology I was talking about before. And then we have a layer thickness. So this is going to be a possible stratigraphy that is going to reproduce what has been done before in modeling and observation studies. So with this on, I'm going to show the results for the modeling. So I'm going to show two slides, the best case scenario for flow and the worst case scenario for flow. This would be the maximum velocity that we would get considering this sort of like layered flow structure. And now we're considering that all of the layers are deforming. Because all of the layers are deforming, we actually can see that the velocity is building up throughout the NPLD. And essentially what dust layers do is stiffen the flow and prevent it from flowing much. But still the whole thing is deforming, and you see that the velocity is gaining us. So under these conditions, we get about 10 meters per million years, which is still very, very slow flowing. However, in comparison with the next step, which is what happens if all of the layers are dust rich, and what happens is like velocity goes to zero at each ice and dust rich layer interface. So of course, this is not going to be realistic. The previous one is also not going to be realistic, but this offers us the minimum possible velocity of the NPLD, which is actually going to be order millimeters per million years. This is unobservable. There's no way that we're going to see this with HiRISE or with radar, just not enough resolution. So in this case, what we're going to see is that each one of those layers is going to bring back the velocity to zero. So at the end of the day, there's no integration of the velocity. It cannot grow, right? So this effect of dust-rich layers is disproportionate if most of these layers actually were to be concentrated near the base of the NPLD, which is what I showed before. Most of the deformation of the ice deposits happens near the base. So if here we accumulate most of the dust layers, then the total effect is going to be that we're actually near the worst case scenario for NPLD bug flow when the dust is accumulated at the base. So layers with higher dust contents are likely actually found towards the NPLD base, as has been shown in modeling studies. And these are not going to deform. So at the end of the day, we're going to expect velocities around centimeters per million years. Yeah. So I am going to quickly go through my conclusions since I still have a few seconds left. So essentially, the lack of observable deformation in the NPLD on radar or in high resolution imagery can be explained by its layered nature, and also by the fact that particularly near the base of the deposit, we have a lot of dust-rich layers that are going to be very brittle and are going to be rigid and are going to prevent velocity to be gained near the base of the deposit. So the flow rate we are expecting is going to be centimeter per million year. Thank you.
Thank you. Last speaker is going to be Luca Guallini on first radar evidence of large-scale glacial folding in the South Polar Layer deposits, Ultima Scopuli, Mars, unveiled by Marses.
I can't find the remote control. Oh, sorry. Yeah. So, hello. So today I'm presenting the first radar evidence of large-scale glacial folding in the subpolar layer deposits on Mars. So we are in the southern polar ice cap, and in particular, we are in the Ultima Scopuli ice sheet, where we have the subpolar layer deposits unit that is composed mostly by an alternation of water ice layering, plus variable content of dust, around 10% in average. The thickness of this unit is about 1,500 to 2,500 meters, while its age is dated to the late Amazonian. So as all we know, the polar caps on Mars are similar to those on the Earth in some way. These caps are basically studied with the use of radio echo sounding techniques, in particular with the use of airborne radar sounder that operates in general with a vertical resolution of some meters. So the radars emit radio waves that penetrate the ice caps, and in function of the dielectric discontinuities, we can observe the internal stratigraphy and the eventual presence of geological structures. So as said in previous talks, on Mars we have two radars. One is the Mars Advanced Radar for Subsurface and Ionosphere Sounding, that is MARSIS. The other one is the Shallow Radar, that is SHARAD. For the present study, we only use MARSIS because in the SPLD, in the study region, in general, it's the only one that is able to penetrate down to the bedrock. MARSIS is on board the Mars Express spacecraft and operates with a vertical resolution of 55 to 75 meters in ice and with a frequency of 345 megahertz. So MARSIS has more or less one orders of magnitude or more in terms of resolution lower than the sounder radars on the Earth. However, it is able to distinguish the internal stratigraphy of the SPLD. This is an example where we can also distinguish the topographic surface, the bedrock, and the internal layering. Also, we can observe a particular surface that we call the H1, that is dividing the sequence into minor order units, the bottom one and the top one. This surface is spread over the region. So in the study region, we analyzed several hundreds of MARSIS orbits. We excluded those of low quality, and we found around 19 orbits that show disrupted stratigraphy. Let's see some examples. The first one is the 19188, in which we can observe two clear dark areas or not reflecting areas, NRA, that are interrupting the lateral continuity of the layers. These features are 15 to 20 kilometers broad, and they have a thickness of 1,500 meters, more or less. Also, we can possibly see some tilted layering, but it should be noted that this kind of radargram is typically unfocused one. So to improve the layering visualization, we adopted a focused technique that has been implemented by one of my co-authors, that is Roberto Rosei. In this way, it is possible to observe further layering inside the radargrams, and it is obtaining by summing in a coherent way, in a phase, all the reflected waves at nadir and off nadir. So in this manner, it is possible to recognize further structures and layering inside the NRA zones like this one. These are some examples in which we can distinguish some circular shaped features that we call A-folds-like structures. Other cases came from the core of the region. Here there is the 10737, in which we can distinguish again some particular features that are similar to the previous one. In particular, in the focused radargrams, we can see something like this, circular shaped to convolute shaped structures. We can see them at both frequencies. Here there is an example, and the other one is on a parallel track that is close to the first one, where again we can see some circular shaped features. Another case is the 14948, in which in this case, we can distinguish again in the focused radargram other kinds of structures. In particular, these structures has an antiform fold shape, and they have an amplitude of about 1,000 meters in the SPLD. It should be noted that all these last structures lies above the putative Baselwater region inferred by Orsay et al. In 2018. However, they are not exclusive of this region. In fact, we can see other deformations at the borders of the study region. Let's see some other examples. This is the first one, in which we can note a bedrock relief that is affecting the overlying stratigraphy. These structures is not visible in the unfocused radargram. However, in the focused one, we can distinguish a sort of an antiform shape fold. Other similar cases are at the opposite side of this region, where again, we can distinguish a bedrock relief that is clearly affecting the SPLD stratigraphy, and we also recognize again some iForce-like shape feature. So to understand if this kind of structures could be real geologic structures or could be real to radar artifacts, we adopted some methodologies. The first one is to verify if the cross-cutting radargrams at different frequencies are showing similar features under a different point of view. And as you can see here in this example, where you can respectively see the in red and orange two cross-cutting radargrams, they are showing similar features and array zones and tilted layering at both frequencies. Also, we modeled the radar signal. In particular, we simulated the radar scattering at molar resolution created by topography. And as you can see here in this example, the simulations are completely clear. We don't have any radar scattering in the radargrams. Finally, we compared Charade orbits with MARSIS-1 were existing. As said, Charade is not able to penetrate in depth in the SPLD in the study region. It penetrates down to 500, 600 meters in general. However, in some cases, just on the vertical of the MARSIS structures that we observed, it is possible to observe something like this, a mild folding in the overlying stratigraphy as indicating a buried geological structures that probably is affecting the overlying stratigraphy as it occurs in similar cases on the Earth. So we can say that probably these MARSIS structures could be real geological structures. As actually is on the Earth, where sounding radars with a better data and resolution, of course, they are showing similar features, for example, in the Greenland ice cap, and showing them face-to-face with MARSIS structure, we can see that they have a similar, a comparable morphology and a comparable size than those of MARSIS. We can recognize N-array zones, folding, and I-folds, and broad and complex deformation areas in the SPLD. So on the Earth, in sounding radagrams in ice caps on the Earth, these features are interpreted to be related to real geologic structures in sheared zones that are caused by the outward movement of the ice cap driven by gravity and along the attachment planes. This movement causes differential stress that in turn results in the formation of asymmetric faults, in particular overtuned and recumbent and sheet faults. The sheet faults mark the highest flattening, the highest strain rate of the layers. And the I faults that we observe in MARSIS radargrams and in the sounding radars on the Earth are a particular case of sheet faults, or more precisely, they are a 2D cross-section of the real 3D shape of a sheet fold. Here on the right, we can see an example of I-fold in a rocky formation. So in summary, we can say that probably we found the first radar evidence of glacial folding on Mars and as a consequence in any planetary bases, as far as we know. These structures have the same morphology and a comparable sites than those on the Earth, and they develop in the lower third and starting from the bedrock in general. These faults also entail an outer movement of the ice cap driven by the gravity that probably occurred during the past. These arguments are part of a publication that we are
10
submitting.
seconds.
However, we need further analysis to understand the exact mechanism of formation of these faults and their geological and kinematic condition. We have evidence of bedrock influence in their occurrence. However, it is also possible that wet condition, especially during the past under warmer condition, could have favored the movement. So we have to indicate about the geologic scenario. Thanks.
Thank you very much. We can now start our Q&A. It's going to be 25 minutes. If you are in the room, you can use either of the two microphones. Remember to state your name and affiliation.
Give us a notice at 5.
Hello. My name is Trevor Austin. I'm from Arizona State University. My question's for our session chair that presented. Sorry, I didn't get your name. So it occurs to me that during climate episodes where Mars is covered by more ice, there should be less contamination from dust. Correct me if I'm wrong. So does that mean during those episodes the ice will be more flowy? And do you think we would see any evidence of that on Mars today?
Sorry, I didn't pay attention to the last bit of the question. Could you repeat the last bit?
Do you think that during the episodes where Mars is covered by more ice, it'll be more flowy and we'll be able to see evidence of that on the current surface?
So there's two things that are going to accelerate the flow. One's going to be warmer. So the viscosity of ice is highly dependent on temperature. You have an exponential decrease in viscosity. If you have more accumulation of ice, you will have thicker ice layers, and that will also like enhance flow within those ice layers. So it's very possible that wherever you have thicker ice layers, you will see more flow. But even in that case, the key thing here is that if you have these dust-rich layers, your flow is going to go back to zero at every interface with those layers. So really like think about squeezing a cake. Like, you know, the cream is going to flow out. But at the end of the day, the whole cake is not deforming. It's just the cream layers, right? So the thicker the layer, the more deformation, sure. But it will still go back to near zero where you have these very rigid layers.
Thank you.
Good morning. My name's Lydia Ellen Tonani Peña. I'm from the Worcester Polytechnic Institute in Massachusetts. My question was for Stefano Nerozzi. I wanted to ask which software you used to make the phase diagrams with the lithic content with water ice, basalt, and gypsum.
It's a Python script that I found online. I can give you the details later.
Yeah, I'd really appreciate that because those diagrams are one of the best ones I've seen thus far.
Yeah,
like they're really beautiful.
I did next to nothing. The Python is a library I found online.
All right, thank you.
Hi, Shannon Hibbard, Desert Research Institute. I have two questions. Isaac, I'll start with you. Do you have any idea about the timing of the unconformity or disconformity? Do we have any sort of model that might predict that?
Yes, I didn't say it, but I think that 1.8 million years might be the time frame for that one.
Ooh.
And if that's true, that might make the cap look a little older, but we don't know the accumulation rates through time. So
Yeah.
somewhere in that 1.5 to 2 million years.
That seems young though, doesn't it?
If the bottom of the cap started about 4 million years ago, then this is more than halfway up. So it's closer to the top. And so I would expect 2 million years to be halfway. But if the accumulation rates were higher early on, then you could push it towards the top.
Okay. But also wouldn't, sorry, I'll do my second question after you all. Wouldn't I mean, I know it's less gravity, but wouldn't the weight shorten the thickness of the deeper layers? And so then halfway wouldn't necessarily be.
You can think about densifying, and certainly on Earth, the fern layer will densify as you go in like the first 100 meters, but below that, it's pretty much as dense as it gets.
Yeah.
And we think that on Mars, the ice deposits more densely. And so the fern layer is only centimeters instead of hundreds of meters or 100 meters thick. And so it's probably reaches maximum density very quickly, close to the top.
Cool. Thank you.
Hi, Reed Parsons, Fitchburg State University in Massachusetts. My question is for Anna. I am wondering with these dust layers that you're setting the velocity to 0 at, if you're assuming that there's some cohesional strength to that dust layer then, right? So if it is unconsolidated dust that is in between these ice layers, could we not still get that dust to deform and be carried by the ice that's deforming underneath it? Can we still integrate velocity vertically?
So I spent a lot of time scratching my head about what the rheology of dust was. Turns out that in 2002 and in 2009, there's a couple of really nice experimental papers that look at the rheology of dust-ice mixtures with implication for Mars. So there's Mangold and Durham that looked at that. And they both reported at different temperatures a jamming transition at a dust fraction of 0.67, slightly temperature dependent, but more or less around that. And at that point, actually dust-ice mixtures that in principle are cohesionless, they actually become cohesive. And there's a transition into like brittle behavior. And that's why I sort of like separated dust, like icy dust layers, which are deformable, to dust-rich layers, which are jammed and are not deformable.
I guess what bothers me is that the dust-rich layer is under tension, right, as the ice is being spread out underneath it. So I feel like it should be weak enough to still break.
So I also scratched my head, and we can discuss this later also. But I looked at the brittle behavior of what happens if you have like dust-ice mixtures under compression subject to tension. And it's complicated, but there's some permafrost studies that look at some of that. And it's going to come up in the model also, the brittle behavior of it. But in principle, they shouldn't break that much.
Hi, my name is Dan Lalich from Cornell. I'm sorry I didn't write the name down, but I have a question about the outlier deposits. So I mostly work with the polar cap. I'm familiar with the crater deposits, which I understood to be stable because they're in these little microclimates. How did these outlier deposits that are just kind of sitting on the surface like get there? And what should we, like, what's their relationship in terms of like age or timing to other ice deposits?
Yeah, that's a good question. There's still a lot of unknowns about these outliers, and we still have a lot to study. I think, I don't know if it's been directly hypothesized in other papers, but I know there's a couple ones, just like accumulation and also maybe like a remnant of a larger PLD. Again, we don't know. We would assume that they have to at most be the age of the PLDs, right? But they're probably younger, especially the three weird ones. The ones with higher permittivities, though, because they have a higher dust content than the PLDs, they're probably slightly older than the other outliers because they've been sublimating away for long enough. But yeah, there's still a lot of questions that we are trying to figure out and answer about them.
Hi, quick question for the last presentation. My name is Rashika Paranla from Princeton and NASA headquarters. So there's this evident analogy between physical phenomena on Earth and Mars. So I was wondering, in your opinion, can we say that high permittivity associated with the bright regions on Mars is directly indicative of water saturation layering, or like to what extent?
I'm sorry, I didn't get your last words.
Sorry?
I didn't get your last words.
Yeah, so the high permittivity detected on bright areas of Mars, is that directly indicative of water saturation and layering, or to what extent?
I think this water saturation of layering, like something like this, but probably something like some process related to basal melting, I guess. But I mean, I don't want to say that these structures are demonstrating that we had water at the base of the ice cap, because it's possible also dry processing in the formation. But as it occurs on the Earth, it's possible that melting processes at the base of the ice cap that could favor this kind of movement. And so they can saturate maybe sediments at the base of the ice caps and favoring the flowing of the cap.
Okay, thank you.
Welcome.
Shannon Hibbard, Desert Research Institute. This question is for both Anna and the last speaker. I'm sorry, I don't remember your name. Anna, I think in your talk, you had mentioned that the radargrams of Greenland, where it showed deformation, it was radar clear. I don't know what to call that. And then we saw what I thought looked kind of similar in your talk, and then you interpreted that to be deformation. So I'm curious what your thoughts are on that.
I think before we got to the resolution where we could actually see the folding happening, it would show in the radiogram as like echo-free zones. So you couldn't find the structure, like you just kind of like saw like a blurry. And this is exactly what you're showing in the SPLD, and you were able to resolve.
Yeah, exactly.
That was really cool, actually.
Yeah, thanks. Yes, because in general, you can just see, depending on the resolution, black areas, dark areas that are dimming areas with no signal. But improving some techniques, it is possible in some way to resolve these zones in order to define more layering, and maybe they are consistent with those on the Earth. Obviously, the resolution is completely different, so the definition of Martian structures is not so good like those on the Earth.
Yeah. Cool, thank you. It was cool to see kind of the similarity drawn between, or the
Yeah.
parallels drawn between
Yeah.
your two talks. Thanks.
Allow me to just quickly interject with a question for Mai. Yes, you can. Yes. So I was actually wondering, like you're looking very nicely at the accumulation of this dust and ice layers, and I'm wondering if you can see like the time effects, like what happens as you accumulate over the years. You see any difference in any of the characteristics you're looking at between like freshly deposited and slightly older layers?
I don't really think we can see that, at least in Cassis, because in Cassis I have year 30, 35, 36, 37, and it's quite the same at the 3 years range. So I would say no, but probably if we have more, maybe yes. But in Cassis, 3 years is not enough to answer that question.
Thank you.
Yeah, thank you. This is Matt Chinaki from Planetary Science Institute. Yeah, same speaker on Loth Crater. I love Loth Crater. It's a fantastic study area. One thing I wanted to ask you about was the dune field that's on the perimeter there. It's partially buried in ice, and it's also active. So there's kind of a diffuse margin between the ice and yes, as you're aware. So some of the sand is under the ice. Some of the ice is maybe translucent. So how does that, how do you deal with the photometric properties of these different images? And related, sand is saltating in the late spring and early summer. It might be going on part of the deposit. How do you kind of untangle sand from dust and ice?
Yeah, so that's quite complicated to untangle the two. So the Cassis images are calibrated all in the same way, but what you can see is that the closer to the edge you go, the bigger you have a kick in blue. So the ice is quite more pure if you go away from the sand dune. So because I'm looking at the patches in the center and quite eccentric for the sand dune, I don't really have this problem. But if I were closer to the sand dune, yes, it gets very complicated. And if you look closer at the clustering, so the K-mean clustering I did, clusters are not good close to the sand dune because of that mixing. So that's indeed a quite complicated area. That's why it's called like irregular and trough bearing ice, because everything is mixed. And that's quite complicated to untangle from just free filters pictures. And yes, it does move from year to year as well, because just Aeolian movement of the tube. So.
Great, thanks. And by the way, we're getting plenty of high-rise data throughout the spring and summer. So, yeah.
Cyril Grima from UT Austin. I have a question for Luca. Luca, so you observe those structures on the radiographs of Marsis over Ultimi Scopuli, right?
Yeah.
Is it because you restricted your study to that area, or because you don't see them elsewhere over the cap?
I'm just focused in that area, but I'm trying to widen the study region in other parts of the ice cap. Unfortunately, Mars is not always able to distinguish clearly the internal layering. For example, in Prometellingula, I try to observe Mars's radagrams, but you cannot clearly distinguish the internal structures in this moment. So I'm trying to do something similar.
Thank you.
I'd like to follow up on that if I can. There's lots of observations of Marses at the North Pole. Do you see any evidence for similar features at the North Pole where the Sherrod data can corroborate?
Yeah, I know. I didn't check, but honestly, because it's the opposite. Sherrod is not usually able to see layering in the South Polar layer deposit, but then in Prometellingula, it's able to distinguish clearly the stratigraphy. But in the North Polar region, Mars is generally not able to see something. It's very fuzzy. You cannot distinguish internal layering, so it doesn't work.
It'd be nice to have a direct comparison.
Yeah, I know.
My name is Roberto Aguilar, University of Arizona, and I have a question for Luca. If you have this subsurface topography, at least with Sherrod, if this topography or this glacial folding happen to be in the cross-track direction, you will get some subsurface clutter. But if you are in the along-track direction, you wouldn't see any clutter coming from the side. Have you done any subsurface clutter analysis to actually validate that topography?
With Sherrod, you mean?
Yeah, with Sherrod
No,
or Marsis?
no, not yet. No, I just did cratering study simulations of the Marsis radargrams in order to define the cluttering created by the topography at molar resolution. That's it.
Just a follow-up question, but that's the topography at the surface, not
yeah, at the surface, yes.
Okay, not a hypothesized topography at the base.
No, because it's quite tricky, because it's not easy to reconstruct, to observe the basal topography at enough resolution to do sort of the cluttering simulation.
Okay, thank you.
This is the problem.
Adrian Broquet-Dialon. I also have a question for the last speaker. So I don't think we see the features that you've shown in the North Polar Cap. And if it's not an observational bias, is it a difference in ice biology and composition and layering of dust?
Yeah, the age of North Polar Caps, the North Polar layer deposits, the North Polar layer deposits are younger than the South Polar layer deposits. This is the first reason. And so they are probably composed, they are both composed of water ice layering, but there is something different in terms of composition, structures, and rheological condition, and so on. So you cannot observe similar features.
But just to follow up, we've seen flow rates of at most centimeters per million year, right? So even if you had a 10 times age difference between the two ice caps, I don't think time would be the explanation there.
So perhaps I can follow up into that. I think it matters what the layering is like, because if you have layers like, if you look at the bulk composition of the SPLD, it's more dusty. But perhaps the way in which the dust is accumulating in the different layers matters a lot in what the rheology is going to be like.
In the internal structure, I mean,
In
of the
internal
layer,
structure,
yes.
yeah. So if you have layers that are, perhaps you have less dust overall, but you have layers that have higher dust contents, that you have more accumulation of dust in individual layers. And that will stiffen the deposit versus if you have more dust, but it's more homogeneous. And then in that case, it will still be able to flow. So it, you know, like that's kind of like, I think what comes up from both of our talks, like the SPLD is deforming and the NPLD is not.
Yeah.
And I think one of the reasons could be the composition of how and where the dust is distributed. And I think that matters.
I forgot to say that in the SPLD, there is also some clear evidence of deformations along the scarps of the SPLD, not in the same region, but in the promethylingular region. You can see broad and complex deformation areas that are suggesting that the ice was moving. Yeah, I listened. Yes. No. Just the, yes, exactly. The internal part of the ice cap. Yes.
I have a comment on this too. The SPLD and the NPLD probably have also very different histories, very different ages, and the conditions experienced by the SPLD in the distant past may not be the same that the NPLD has experienced over the last few million years. So temperatures could have been higher and allowed for flow that is not happening currently.
And maybe also the rheological contrast between layering it matters. Yeah. Yes.
These will be the final two questions. We have 5 minutes left.
Awesome. So Margaret Landis, Laboratory Atmosphere.
Try the other one. Yeah.
Maybe.
Okay, I'm not going to touch this one and hopefully it will work. Margaret Landis, Laboratory for Atmospheric and Space Physics. First, a shameless plug to go off Matt's comment about high-rise is still imaging. If you need high-rise images, please submit them through the HiWish tool and then email me and I will prioritize them. I think the Louth work is really interesting. And so, yeah, definitely get in touch. We can make some stuff happen within reason if you need it. And maybe to kind of sharpen the point that I think the discussion is getting to here about the SPLD, my question is, given that we know that likely the Dorsa Argentea formation is arguably an old polar cap, and that Coleman Tanaka 2006 found at least one major deflation and kind of resurfacing event over a lot of the cap, what kind of data or additional tests could we do to understand the age at which this layer that was probably deformed actually formed under, to tie it back to some sort of climate conditions?
Well, basically, the main instruments are the radars, I guess. However, I'm trying to search for possible evidences using images, CTX, and maybe IRIs as well, to understand if there is some evidence along the scarps. In this region, there are deformation structures that are called LAPS, LAPS, that are suggesting maybe with some faulting structures that this zone, it was deforming. So I'm trying to do some tests using optical images or something to cross the data set.
Awesome. Well, please get in touch. Jenny Witten and I did a geomorphic map of the region a couple of years ago, and we'd definitely be interested in teaming up if you would be interested in that.
Okay, thank you.
This is Matt Shinaki at PSI again. For the outlier discussion of those polar layer deposits, you had a cluster in your abstract at close to 70 degrees south or a little further south. So maybe just talk about, like, is that normal for crater polar layer deposits? And is that extreme in latitude? And then just what's the texture of these things from CTX and high rise?
Yeah, that's a good question. A lot of them are at lower latitudes. The three that have the lower permittivities are at that like 70 latitude. And then in the southern hemisphere, they're all around like 70 as well, even down into like 65 latitude. So that's pretty common. And then wait, what was the last half of your question?
Well, is that common for the polar?
Oh yeah.
The crater confined polar deposits.
Yeah. So the crater ones are also at those latitudes as well. So Burroughs is right next to one of the ones in the southern hemisphere, and then Louth is next to somewhat close to that as well. And we haven't looked a whole bunch at high rise and CTX yet, but they all have layers for the most part, but they do look different between the two hemispheres. And they aren't as like, they're a little bit more flowy, I guess, and less sharp and like rigid like the PLDs.
Okay, yeah, I'd also suggest getting stereo there too.
Yeah, for sure.
Thanks.
I have a couple more questions for you, Brian. Did you see any evidence of internal layering in SHORAD data? And did you attempt to use higher resolution DMs, perhaps captured by HRC or made with CTX stereo for further clutter validation?
Yeah, we saw layering in several of them. The Olympia Mensae, the big one in the northern hemisphere, and then all of the ones that we could see in the southern hemisphere with radar also had layering in them. We haven't looked too deep into that part, like the internal layering yet, but we do plan to do more investigation, especially for the like paleoclimate studies. But yeah, there is internal layering, which is really cool.
Very quick follow-up. Just a follow-up to this question. We do have gases on the Olympia Mensae one, so the big one, and we have seasonal variability as well on this one, and we can very nicely see the layers in this one as well. So please let's team up because we have kind of cool gases images of
sure.
this one. So it could be cool to see if there is the same kind of spectral variability I see in loose in this one.
To
That's it.
respect everybody's time for lunch, that's going to be it for questions. Just to remind everybody that the poster session is at 6:30. The Mars Polar ones are between 390 and 410. There's 17 posters, so go look at each one of them. And if you are a Mars Polar grad student that went to conference last July, we're going to meet up for drinks afterwards at Goose Acres. Have a good lunch.
Yeah.
I was going to close it and she was like, on it.